Today we want to upgrade finding the slope of a line tangent to a function at a given point to finding the equation of a line tangent to a function at a given point. So here's a quick review of just equation of the line stuff. And this first form here, this variation, this function form of the point slope equation, y equals y naught plus m times x minus x naught, is the one that we're going to want to use because it focuses on the point x naught, what's going on at x naught. So the calculus part says use the derivative to find the slope. That's the new thing that we add in calculus. So the calculus contribution is just going to be to use the derivative to find the slope. It's another way that we can find the slope. Rather than taking 2 points and looking at the change in y divided by the change in x, we're going to use the derivative to find the slope. This is going to be important because if you think back to finding the slope of the tangent line, we only get 1 point, and the slope wants 2 points. It wants a delta y over delta x. But if we try to plug 1 point into that, we get 0 over 0. We've got to figure out, our job is to figure out what 0 over 0 is equal to in our tangent line case. Let's do an example. So here's our classic example. Y is equal to, f of x is equal to x squared. And I want the equation of the line tangent to this curve when x is equal to -1. We want the equation of a line, which means we need a point and a slope. We want the equation of a line, which means we need a point and a slope. Because we're looking for a tangent line, we're going to use the derivative to find the slope. That's calculus entering into the problem. One of the things we definitely need is a point, and right now we've only got half a point. Right now we only have half a point. We just plug in to find the other half of the point. So x naught is equal to -1. Y naught will be f, the function evaluated at -1. We need to calculate a slope. For that, we're going to need the derivative. So f prime is 2x. We use our cool derivative finding techniques. And then the slope of the line will be f prime at -1. So 2 times -1 -2. Now we've got a point and a slope. We can just write into the formula. Y naught plus m times x minus x naught. Oh no, I didn't decimal. So here's a graph of our parabola, y equals x squared, and our tangent line. We can see if we multiply this out, we got a y-intercept of 0, -1. So I could also write y equals -2x minus 1. And that's what we would get if we would multiply out our point slope equation. I just realized I can't point here with my pen and have it show up on the screen. I don't know how technology works. And if I move the pointer off, it stops being like a Mickey Mouse hand with an extra finger. So if I want to point at stuff, nope, generic pointer unless you're specifically choosing a point. So, Desmos is messing with me. Aha! Multiply the -2 times the x would be the -2x. And I have -2 times the +1 is -2. 1 minus the 2 is -1. Any questions? If we wanted to do this at some other point, we have the same function, f of x equals x squared, but x naught is equal to 3. Then I'm just going to move my stuff over. I need a new point. If x naught is 3, that means y naught is just the function at x naught. So f of 3, which is 9. Our derivative is still the same. F prime of x is still 2x. And so our slope will just be f prime at x naught, which is f prime of 3 or 6. So our equation of the line, y equals y naught plus m times x minus x naught.
Yes, stream of mass angle.
Normally, I don't expect math to have that much of an effect, but I forgot I cast calculus as an AOE. So. Since we use the same function, if we go back to our graph, we can include, let's see, 9 plus 6 times x minus 3. Oops. There we go. There's the point, 3, 9, x naught and y naught. And here's our slope. We see our slope of positive 6. You see our y-intercept way down here at 0, negative 9. So if we go over 3, we've gone up 18 for a slope of 6. Any questions? Is everybody okay? Yes, find the equation of the line. Yes. I just made that up. I said find the, because I have to tell you, find the tangent line to a curve. So I have to give you a curve at a given point. So So that raises an important question. Why do we care about this tangent line business? Who cares about this tangent line business? We have a function. Why do we care about where it's headed? So one of the reasons we might care about tangent lines is that we think of a tangent line as the best linear approximation of a function at a point. So the tangent line is the best linear approximation of a function at a point. Tangent line is the best linear approximation of a function at a point. Sometimes instead of at, we will say near a point, but that requires me to remember to say near. One way we want to interpret this is that if we zoom in close enough, everything looks flat. That's one of the things that we want to think about when we think about this. When you zoom in close enough, everything looks flat. Or instead of flat, we should say linear, because flat is more of a slope 0. If you zoom in close enough, everything looks linear. Everything looks flat or straight. Some of you are thinking everything. As I go, I know what you're thinking. You're thinking, what if it's not differentiable? Everything differentiable looks linear. When you zoom in close enough, everything that's differentiable looks linear. It all looks like a line. We go out into a large field and say, look how flat this field is. And the earth is just like you're just zoomed in really close, tiny human, for I am massive. That's the earth talking. That's how the earth talks. It's very strange. Oddly enough, it's in English.
The majority there.
So if we go back to our picture, if we go back to our function, there's that red y equals x squared. Right now, we can see that the y equals x squared, definitely not linear. There's this parabola, it's going in two directions, like all down then up again. But if we zoom in, if we restrict our view, the closer we get, the more the parabola just looks like a line. We can tell it's not a line because we know that the blue line is in fact a line, and this red parabola is clearly bouncing off of it. But if we zoom in more, it bounces less. And if we zoom in even more, we don't even have enough resolution to see the difference between the two. Moreover, we aren't even that close. We have not even got that close. This is from negative 1.03 to negative 0.97. So this is still 300ths on either side of -1. If you're thinking that's just because the resolution is proto Game Boy up on the screen here, I assure you, even on the screen that I'm looking at, which is more Game Boy Advance, I can't see a difference between the red parabola and the blue line. If you zoom in close enough, everything looks linear. Everything differentiable looks linear. So even though if we take the long view, if I reset, if we can see that there's this red parabola and this blue line. That's the view from space. We could see, oh, it's round, or in this case, a parabola-shaped world. But if you just think about the tiny humans sitting on the surface of this parabola, they're like, oh, look, we are on linear ground, and everything looks flat. Any questions? Has anybody been to the Midwest? It super looks flat. It's kind of creepy. Like in California, like if you look around on a clear day, you'll be like seeing mountains or hills or some kind of feature. But when you're flying over the Midwest, it's kind of creepy. You look out and it's just flat. I guess I shouldn't characterize the whole Midwest as being creepy, but it is awful flat. If you're from the Midwest, you have to admit flying into Chicago is weird because you could just see it's just flat for as far as you can see. Weird. Any questions? This is pretty handy because our default mode of thinking as humans is to go for linear anyway. If we're going to split the difference, we make a linear function between the 2 points and we just follow it halfway down. I mean, I don't. So like if we're trying to bargain, normal people be like, oh, well, I'd like 5,000 per person says, well, I'm only going to pay 3. Let's split the difference at 4,000. But see, if someone's like, oh, I'm at 5,000, I'm at 3,000. I'm like, well, let's split the difference, but geometrically multiply the two and then take the square root. And they're like, oh, what? I'm like, well, I'm a mathematician. I assure you, this is the best way. But that's only because I was coming in at 3 and they were up at 5. You know what I mean? I'm just kidding. I split the difference normally, like everybody. Because averages are best. Actually, that's false. Averages are terrible. The average human being has 1 ovary and 1 testicle. What? I mean, if you just add them all up and then divide, that's what you come up with. Right? That's average. That's how averages work. Right? No? Averages are terrible. Like, what if you're calculating averages and everything's supposed to be okay, but you got a 0 on that first assignment? Yeah, well, averages are awful. What if everything on that 0 assignment that you got, that 0 you got on that first assignment, what if everything that was on that assignment you have repaired and you now know? And if you did it again now, you would get 100 on it. In a land of averages and unreasonable slavery towards averages, must calculate average. I mean, that's just horrible grading. You know what I mean? Averages are trash. Anyway. Let's talk about a different style of function. Let's suppose that I give you some weird information. Suppose f of 3 is equal to 5 and f prime of 3 is equal to -2. I haven't told you what this function looks like, but I've told you what's going on at 3. F of 3 is equal to 5. I've given you a point. I said that this function is decreasing at a slope of -2. Got a slope of -2. With this information, we can build a tangent line. So x naught is 3. That's the information I've given. And y naught is equal to 5. And our slope is going to be -2. So we can build a tangent line. 5 minus 2 times x minus 3. Y is 5 when x is when x is 3. And y is decreasing by 2 every 1 unit. That's what this equation is telling us. We can use this information to approximate what's going on near 3 on this function. If I wanted to approximate f of 3.1, I could think, well, 3.1 is pretty close to 3, and that's the best information that I have. So I'll just plug this into the tangent line. And I'll say y, so f of 3.1, start down here, will be approximately 5 minus 2 times 3.1 minus 3. We have a slope of -2, so if the function is decreasing, approximately decreasing by 2 when x increases by 1, we just want to know how much x is actually increasing by 0.1. So we should expect y to decrease by 0.2. Questions? We want to approximate f of 2.8. If this is all the information that we have, we could say, well, 2.8 is close to 3. So the best we can do is use this information. So we'll say f of 2.8 is approximately equal to 5 minus 2 times 2.8 minus 3. There's that difference. We're going to subtract or add m every x units or every run units. In this case, our run is 0.2 or -0.2. So we should expect f of 2.8 to be near, be approximately 5.4. Because if x increases by 0.2, y should decrease by twice that, because our slope is -2. The further away we go from the point, the more unreliable this information is going to be. We know what's going on at 3. This raises the question, how far away can we go? And the answer is, unfortunately, it depends. It depends on how accurate you need to be, for one thing. It also depends on what the function is doing. Like if 3 is right near a point where we know the function is turning around, maybe a little bit further away from 3, and the derivative goes from -2 to some positive value, and things are going to start increasing again. So we don't have that information. So how far away we can go depends on the situation. Any questions? I'm going to give you an additional piece of information using a phrase that I haven't even spoke at this point. Let's suppose that I have f of 3 is equal to 5. That's what we knew already. F prime of 3 is equal to -2, but I have additional information. F double prime of 3 is equal to 4. Ooh. Introducing things in an example without even talking about it first? Heck yes. I know that f prime of 3 is the derivative, but now I have 2 primes on this f. I have f2 prime of 3, f double prime of 3. So we pronounce this f double prime of 3. So now we have to talk about derivatives and the order of derivatives. F prime of 3 is the first derivative. What's the first derivative at 3? What's f double prime going to be called? The second derivative. Math is so predictable. It was worse in the beginning. So, well, what are we going to call this second derivative? And we were coming up with all kinds of names. Well, let's call it Francis. That's a good name. That guy got kicked out of the meeting. We're just going to call it the second derivative because it's the one that happens second. It's just the derivative of the first derivative. It's just the derivative of the derivative. The slope of the slope. So the way you pronounce that symbol is say f double prime. That's how you spell it. If you want to read it without just spelling it, you'd say second derivative at 3. I have second derivative information, so I'm not going to make a tangent line. I have second derivative information, so we're going to make a tangent a parabola. Let's just call it that, tangent parabola. I'm going to highlight the fact that a linear function is a first degree polynomial. That means its biggest exponent is a 1. This is the same linear approximation we had before. But now with this information, I'm going to say plus 4 we have to divide it by 2, but it's still an x minus 3 squared. This raises some questions. Why did I divide that by 2? A valid question. I'm doing mysterious stuff here. I'm trying to create our best quadratic approximation of the function near 3. And at this point, I've raised a very strange question. Why divided by 2? Oops. The main reason is I like to allude to chapter 10 way back here in chapter 3. Are we in 3? We're in 3. This is the other reason I don't want to multiply everything out to y equals mx plus b. First of all, that's kind of focused around x equals 0, and we might not know anything about what's going on at x equals 0. Using this to approximate, using a linear approximation at 3 to figure out what's going on near 0 is a bad idea. That's pretty far away. I know 3 doesn't seem like a lot to be far away. But we made the parabola and the line pretty close. We were looking at 3 100ths. So if we went 3 away from this, that's pretty far away. So on one hand, 0.3 isn't that far away, and 3 is just like really far away. But that depends too, right? How much for this car? $25,000. I'll give you $24,997. If you're going to argue at that point, just stop selling cars because you don't understand the whole business. You know what I mean? If that's going to cause your business to fail, $3 on a car sale, then your business is going to fail anyway. You know what I mean? So I'm leaving off some mystery information, but this is a parabola where it's centered at this x equals 3. Incidentally, if I had another derivative, a third derivative, I would have a third degree term that I can add and have the best, I'd have a tangent cubic. It would be the best cubic approximation of the function near this point. At that point, I'd be dividing by 6. So you can think about that. Any questions? So the game is find the equation of a line tangent to a function. That's where our focus needs to be. We want to think of the tangent line as the best linear approximation of a function near a point. As we saw in our graph, this only works near a point. That blue line is only any good near x equals -1. That green line is only any good near x equals 3. If we start getting away from 3, like here at 0, it is a very bad approximation. The parabola is like all 0, and the line is like -9. That's way off. Any questions? How's everybody okay? Right, that's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.